All right, this is where we're going to begin our class today. Um, we're still finishing up oscillations in a sense, or harmonic motion, where we're looking at a spring, right? Now, this proof right here is to basically, derive the formula for when we're trying to find the period of a spring that is pretty much a vertical spring, all right? In previous lessons, we'd have looked at the the derivation for when the springs were pretty much horizontal, such as this. All right. This one is a little bit more complicated because it takes into account a lot of things, right? It takes into account a lot of things. Um, I don't think we have to go through this proof mainly, right? But what I want you to see is that you would have started out, if I wanted to derive that equation that says, the period is equal to 2 pi times the square root of the mass of the spring system divided by k, right? Then I would have to start from this notion or this standpoint to say that, all right, so at first I would start out with a regular spring which wouldn't have any mass attached to it. But then now, when I attach a mass to the string, or to the spring rather, what you would observe is that there's going to be an extension, meaning that the spring is going to extend to a certain amount. The easiest way to find out the amount that the spring has extended by, right, is to just measure where the original spring was, and just measure the distance from where it was to where it's now at. That would be your first initial extension value. Mind you, this spring right here is not oscillating, it's not moving. It is just what you call it now. It's just stretched, or some weight is hanging on it. Now, as you can imagine, whenever you have a spring and you apply some level of force on it, such as a weight, it's going to have a force acting downwards, which is what we call mg. And of course, once you're dealing with a spring, there's going to be a restoring force. And generally, the restoring force on a spring is linked to Hooke's law that says force is equal to minus k times x. But in this case, x is what we call E, which is the extension. So for this one, we're going to just write E. So F1 is equal to minus k times E, which is just that extension right here. Now, because the spring is not oscillating, it means that there is no acceleration. And if there's no acceleration, what it means that Newton's second law, which says that the net force is equal to 0. What is my net force? My net force is the algebraic sum of the forces acting on the object, which is F1 and F2. F1 is going up, so that's going to be a positive force. Mg is going down, so that's going to be negative. So if I were to write out all of that, I would come by this equation right here that says, F1 minus mg is equal to 0. The whole reason why it's equal to 0, as we said, it's not oscillating. And because we know F1 as minus Ke, right, that is the restoring force, as I would have stated, then we could have substituted that into this equation. Now leaving us with, an equation that we're going to use eventually that says minus Ke minus mg is equal to 0. And all of this is coming from the whole fact that the spring is not oscillating. Okay? But now, with a further increase in terms of the spring, so if you were to extend the spring further to X amount, then you can imagine now that obviously the restoring force is going to change because you're increasing the extension. Because what you have to understand is that extension is directly proportional to force, and that's what Hooke's law states, right? To say that whenever you have a spring and you extend it, the extension is going to be directly proportional to the force, all right? So in this regard, F2, so F2 is going to be related to the overall extension of the spring, which is basically having to say that minus K, right? In bracket, I'm going to put X plus E. That is going to be the overall extension of the spring whenever you pretty much pull it down furthermore. Now at this point, we're going to make the spring oscillate. So by pulling it down to this amount, we're making it oscillate. The reason why it's oscillating is because the upward force is greater than the downward force. In this regard right here, the second one, B, F1 is equal to mg. So because they are equal, then it's not moving, it's balanced. But once the restoring force is greater than the downward force, then that is when it's now going to oscillate. And if that's the case, then we can come to this conclusion to say that, the net force using Newton's second law, because it's now oscillating, then it's equal to mass times acceleration. And just a while ago, we saw where the net forces would be F2 minus mg equals to ma. All right. So having said this, we just said a while ago that F2, right, is going to be minus K. In bracket, we have X plus E. The reason why we have to add that E is because of that further extension. Because at this point, you would have had an extension here. You would have known that value. Then you would have further extended. This is when you now pull the string or pull the spring further down to extend it to a second or to some amount, some more. And with that further extension, it's now going to result in, having more upward force, right? Which is what we're seeing here, which means that it's going to oscillate. So I'm going to go ahead and substitute this into this equation. Let me know if you have any questions in the meantime. I wonder who dropped off. Campbell dropped off. Talk to me, Rachel. Let me know if you understand anything here.
Yes, sir, I understand. It's kind of the same thing in C said.
Yes, precisely. All right, good. Yeah. So what we're really doing is that we're just trying to prove or to derive an equation. That's what I'm saying. So we're at this point where we're now saying, obviously we would have substituted F2 for minus K bracket X plus E. And we substitute that here, there, we're going to expand it. By expanding it, we're going to take the K that is on the outside and multiply it by, by the E and by the X, leaving us with minus KE minus KX minus MG is equal to MA. Right? Now, if we go back around here and look back at this equation, where we're seeing minus KE minus MG, right? Let's see something here. All right, minus, so yeah, so if we remember that minus KE minus MG is equal to 0. So in essence, if we were to put these two together, right, this goes to 0 because it shows us around previously that this is equal to 0. So what we're really left with is minus kx is equal to ma, right? So that's the reason why we had to do that first part as it pertains to when the spring is not oscillating and it has an extension of E, right? Because we want to get rid of that when we come to this standpoint. So by way of just rearranging it, we can see that minus Ke minus Mg was equal to 0. So hence the reason why we can, pretty much eliminate that, just leaving us with this thing right here. Now, what we want to do now is to transpose, right, to make A becomes the subject, which is pretty much the acceleration, right? So if I were to transpose minus Kx equals to ma to make A become the subject, then my acceleration is going to be minus k divided by m, right, times x. Now, this is very crucial. This is very important because what this is going to show us now is that this acceleration, this acceleration is related to the acceleration for when something is undergoing simple harmonic motion, right? Whenever something is undergoing simple harmonic motion, there's an equation that says A is equal to minus omega squared times x, right? So what this tells us is that um, the acceleration is directly proportional to the displacement. So the more you extend the spring down, if I were to pull the spring further down here, then what you would realize is that there's going to be an acceleration in the opposite direction. And the more extension you have, it's the more the acceleration is going to be, which means that obviously the more the restoring force is going to be, right? But we're interested in talking about the acceleration. So this is your extension, which is pretty much your displacement, right? And then now this is your acceleration here. Your acceleration is going in the opposite direction, which means that you have a minus sign. The minus sign signifies that the acceleration is opposite to the displacement. So while the displacement is going down, the acceleration is going up. So those are the two main conditions for simple harmonic motion. To say that acceleration is directly proportional to the displacement, and to also say that the acceleration is um, going in the opposite direction to the displacement. Now, when we compare these equations, so this is the main equation. When we look at this equation as well, it's also going to show the same thing, to say that acceleration is directly proportional to the displacement x, and acceleration is going in the opposite direction to the displacement. Can you compare and see that these two things pretty much make sense? These two acceleration equations. So this equation that I'm writing here now is a general equation for simple harmonic motion. This is the reason why we can now say that whenever an object obeys Hooke's law, that the object is, or it will undergo simple harmonic motion, and that this equation will apply to it. Now, when we compare the equation, we're going to realize that if I compare A against A, right, I'm going to compare negative omega squared with negative k divided by m and x. I'm comparing them. So what I'm left with now from this comparison is to say that minus omega squared is equal to minus k divided by m. This here is to help us now to derive this equation. If we never compare these two things, right, then we wouldn't be able to can pretty much derive this, right? So this is really where we want to go at. All right. Let me see here. So let me just clear the screen a little bit. Let me know if you have any questions for me though. In the meantime, please also remember that you have to be watching the lessons as well. Now, recall that omega is equal to 2 pi divided by t. If so, because I know that omega is equal to 2 pi divided by t, then it means that I can substitute omega into this equation. So at the end of the day, I'm going to get, and we can cancel out the minus signs because they are on both sides. So it means that I have 2 pi divided by t all squared is equal to k divided by m. I pretty much want t to become the subject. So what I'm going to do, I'm going to expand right here with the square. So I get 4 pi squared divided by t squared is equal to k divided by m. And if I transpose to make t squared become the subject, then t squared is going to equal to 4 pi squared times m divided by k. That's what I would transpose to make t squared become the subject. However, I want t to become the subject. So t is now going to equal to, if you want to get t, then you would have to square root both sides to get rid of the square. So I'm square rooting both sides now. So I'm going to get 4 pi square, right, times, so the square root of 4 pi square times m divided by k. Now, what we're seeing here is that we can use the square root sign. We can find the square root of 4, which is 2, right? And remember, we said that a square and a square root cancels out. So that is the reason why we can come back to this point to say 2 pi times the square root of m divided by k. So this is generally the period, all right, of oscillation whenever, we're dealing with a spring. Let me know if you're all right. Talk to me.
Yes, sir.
You have any questions?
No, sir.
All right, all right. I know sometimes they can ask us to prove these things, right? I know that for a fact. So I mean, don't neglect the proofs. When you do see them, don't neglect them because you don't know when they might ask you to do it, right? Honestly, you don't know. There's something important that we must talk about as it pertains to springs, right? From time to time, we can connect springs in parallel, right? And whenever springs are in parallel, it means that we can find the effective spring constant. Okay? So every spring has a spring constant. It has a what we call, the stiffness of the spring. So depending on what makes up the spring, it's going to have a spring constant. Now, whenever you have two springs that are connected in parallel, and I think we know what something looks like when it's in parallel, we can safely say that the overall spring constant for these combined springs in parallel is given by this equation. So if you see two springs, right, that are connected in parallel, then what it tells us is that the effective spring constant is going to be basically the sum of the individual spring constants. Because spring 1 is going to have a spring constant by itself, spring 2 is going to have a spring constant by itself. Whenever they're in parallel, you just simply add the spring constant. There's a way to prove it as well, right? Um, as you can imagine, whenever the springs are in parallel, what we have come to understand is that they're going to have the same amount of extension. The extension is going to be the same, right? It means that both springs are going to hang at the same level. They're going to be extended by the same amount when the weight is attached to it at this point. So if I wanted to consider the force that is acting on spring 1, then F1 is going to be K1 is going to be equal to K minus K1 times X, and for F2, that's going to equal to minus K2 times times X. Now, having said that, we can consider a thing such as the net restoring force, right? Now, the net restoring force is simply adding all the upward forces, because those forces would be the restoring force. The restoring force is a force that is basically bringing the spring back to its back to the equilibrium position mainly, right? So with that being said, if I want to find the net restoring force, I would have to obviously add F1 and F2. When I go ahead and add F1 and F2, I will just put in these variables to say, minus K1 times X minus K2 times X. Then I can group or factor out the K, because the K, not the K, but the X rather, because the extension is constant. I can factor that out. When I do factor that out, right, I then realize now that the net restoring force F, right, is equal to minus K times X. Because what you have to understand is that the resultant or the net restoring force is basically related to Hooke's law, just the same. So I could say that this F right here is equal to minus K times X, right? So let me just erase it because it might be a little bit confusing, right? So that F on that side is going to equal to minus K times X, where that K is basically that, that effective spring constant, right, for when the springs are in parallel. So far we can say minus K X is equal to minus bracket K1 plus K2 close bracket times X. Now these X can cancel out. When we cancel out these X, we're left with the minus K on this side and the minus K1 plus K2. But this minus can cancel out, leaving us with now K, which is basically the total spring constant, is going to equal to K1 plus K2. So that's pretty much how they derive this, how when the springs are in parallel. And as I said, you can be asked questions related to this. You can also be asked to prove it per se. So pay attention to the notes as well, right there and then. All right. There's also another scenario as well, right? When the spring, right? When the springs are in series. Another thing, I think we know what series is. If we remember anything about electronics, series circuits is when the components are connected one behind each other. So it's the same thing here. But the beautiful thing about when the springs are connected in series is that they will have the same restoring force. The restoring force is going to be the same, right? But what's going to be different now is pretty much the extensions of the spring. So spring 1 is going to extend by a different amount from spring 2, and for that reason, in this regard, we're going to consider the total displacement, right? Because obviously the springs are extending to certain degrees, so we can find the total displacement. We can call it total displacement x, and that x is going to equal to, pretty much x1, which is the extension for spring 1, plus x2, which is the extension for spring 2. So that is when they're in series. Now, as you can imagine, using Hooke's law, this spring here, right, is going to obviously have its own restoring force, which is going to be related to F is going to equal to minus K1 times X1. Then for this one, F is equal to minus K2 times X2. Now, if we transpose to make K1 becomes the subject here, then not K1, X1 rather. If we transpose to make X1 become the subject, it means that, X1 is equal to force, or minus force divided by K1. And if I transpose to make X2 become the subject here, then that becomes pretty much minus F divided by K2. So what I'm doing now, I'm going to take those displacements or those extensions for spring 1 and spring 2 and pretty much find the total displacement. So whenever you're dealing with springs in series, we're looking at the total displacement. Whenever we're looking at springs in parallel, we're looking at the total net force. All right. So my total displacement, right, is going to be equal to minus F divided by K1 plus minus F divided by K2. Now, what we must understand that this total displacement is related to, right? Because what you have to understand is that the combined spring is going to have a total, pretty much a total restoring force, and this big X right here, this displacement X, can be linked to this equation that says, obviously force is equal to minus K times X. If I make X become the subject here, then what I'm left with is minus F divided by K, where this K is the effective spring constant of the spring. So at the end of the day, we're left with this to say that, pretty much right here, if you check this thing right here, you'll see it. Because what I'm really doing is to just kind of rewrite over some of what is here already. But this is what we're now left with, to say that minus F divided by K is equal to minus F close open bracket 1 divided by K1 plus 1 divided by K2. Now, the forces can cancel out, the minus sign can cancel out. When we cancel out those, we're really left with to say that, 1 upon K, which K here is the effective spring constant, is equal to 1 upon K1 plus 1 upon K2. Now, there is a simple, there's another way we could pretty much, this doesn't tell you directly the spring constant. You would have to do a lot of things here to find the spring constant, or the effective spring constant of this spring, right, which is the K value. The easiest thing to do is to find the LCM of this side, or pretty much find that mixed fraction thing. So we're saying that K1 times K2, which would have been my LCM. Now when I take my LCM and divide that by K1, I'm left with, K2. K2 times 1, that gives me K2. Then I would pretty much do the same thing over here, and this would now result to K1. So all of this is equal to 1 upon K. I want K to become the subject. So if I make K become the subject, I will transpose. So I will bring that across, right? And then I'll bring this across. So if I do that, I can literally see that K1 times K2 is equal to K2 plus K1 times K. I want K by itself. So at the end of the day, we can see that K is really equal to the product of the spring constant divided by the sum divided by the sum of the spring constants. I know this is a whole lot, right? And a lot to probably remember, but at the end of the day, if we want to try to find K, that is essentially what we would have to do. Right? I hope you're following doing it, Rachel. I mean, I know this is a lot of information. Do you think you can remember all of this that's going on here?
Yes, sir.
All right. Let me just see something here. I wonder if I have any questions related to that. Um, all right. I don't have any questions related to it, but the most important thing you should remember is the equations, right? It's the equations that are more critical for us to remember whenever we're dealing with springs in series and springs in parallel, right? All right. Okay. Now, to sort of finish off this whole thing about oscillations and so forth, or simple harmonic motion, we must touch on a topic what we call resonance, right? Um, I don't know if you have ever, whenever an earthquake occurs, right? One of the, do you know the reason why earthquakes cause damage to buildings? Do you know the reason?
No, sir.
No. All right, cool. No, there are several reasons, right? And one reason that can cause buildings to collapse during an earthquake is due to a thing what we call resonance, right? Now, everything in nature has what we call a natural frequency, right? Everything in nature has a natural frequency. So a building has a natural frequency. Uh, an earthquake has a natural frequency, and frequency just speaks to the oscillation, right? When you talk about frequency, it's the number of oscillations per unit time or per unit second. So it says to us that whenever whenever you have an earthquake and the earthquake's frequency matches the natural frequency of a building, then what we're going to realize is that there is going to be a rapid vibration, right? There's going to be, it's like whenever the two things clashes together, whenever the natural frequency of the building matches with the natural frequency of the earthquake, then you're going to realize that is when the building is going to oscillate very fast. And if you were to look at it from a graph standpoint, this is what is really happening. So let's imagine that the earthquake is building up. When that frequency reaches the 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 the, the, the resonant frequency of the building, right, or the natural frequency of the building, what you realize, this is how the building is going to oscillate. It's going to vibrate really, really fast, causing this very sharp peak to occur right here. And so, whenever that happens, you can expect that the building would pretty much, undergo a lot of stress because it's now vibrating very fast because of the whole fact that the natural frequency of the the earthquake matches the natural frequency of the building, right? So it says that when an object oscillates without any uh, external forces being applied, it oscillates at its natural frequency. This is what we call free oscillation. So that's just talking about oscillations on a whole, right? Just speaking about free oscillations. But there's a thing what we call forced oscillation, and this is the same thing about resonance. So it says that forced oscillation occurs when when a periodic driving force is applied to an object which causes it to oscillate at a particular frequency. When the driving frequency of the external applied um, or the external force applied to an object is the same as the natural frequency of the object, resonance occurs. It says that this is when the amplitude of the oscillation rapidly increases. And it says that the amplitude will continue to increase until the system fails. Right? It's a very good concept to talk about, but I mean, it can also be a hard one to understand to some degree. But what you just have to remember is that everything has a natural frequency, and if there's a forced oscillation, meaning that if you're forcing the building to oscillate, which is sort of like what the earthquake does. The earthquake is forcibly oscillating, oscillating the building. If the frequency of the earthquake is such that it matches the frequency of the building, then that is when resonance will take place.